In this operations management lecture, we're going to look at forecasting techniques. My students can access the video tutorials for these problems using the content menu in D2L. YouTube viewers can access the video tutorials on my MOOC on udemy.com. I have a long and short version of the URL posted on the screen, and I will post this URL in the description. Let me point out to you that it is critically important that you practice all these calculations that you're going to learn in forecasting. The math is not hard, it's not complicated. However, there are a lot of variables to keep track of as you use all the data and put it in the right area. The only way to make sure that you can keep track of all of that is to practice, practice, practice. Start practicing early so you have time to ask your professor if there are any problems. The first technique we're going to talk about are simple moving averages. While you can forecast one period in the future with simple moving averages, they're mainly used for smoothing out variations in the data before you begin the forecasting process. As such, they're sometimes called a data smoothing technique. We tend to use averages in the 3 to 5 period range. If the data has seasonality, then we would have the averaging period match the seasonality, so quarterly seasonality would use a 4-period moving average. The more periods you use, the smoother the data looks, but you begin to lose your seasonality, and it can be harder to spot trends. With simple moving averages, each period is weighted the same. So the first period is weighted the same as the third period in a 3-period moving average. Simple moving averages assume there's no trend and no seasonality. You see the formula on the screen, but everybody knows how to do simple moving averages. You just add them up and divide by n. So if you're doing 3-period moving averages, you just add up 3 actual demands and divide by 3. It really is that simple. Remember, I have video tutorials on how to work these problems. The screen shows a graph of a set of actual data and a 3-period moving average. The blue is the actual data, and you can see it has a lot of variation. The orange is the 3-period simple moving average, and while it has variation, you can see that it has a lot less variation than the raw data does. Thus, you can see that the variations have been smoothed out. Weighted moving averages are very similar to simple moving averages, only different periods are given different weights. You already know how to do this. Most likely in the course you're taking, your exams are weighted heavier than your homework is. So, when your professor computes your average, what they're computing is a weighted average. Weighted moving averages can be used with seasonal data. So if you had quarterly data, for example, you might use a 4-period weighted moving average where the 4 quarters ago was weighted heavier than the other 3 quarters. So if you're doing summer this year, summer last year would be weighted the heaviest. Simple moving average is just a special case of weighted moving average where every period is weighted the same. This is not required, but virtually every textbook requires that the weights sum to 1. All that does is make the math a little simpler. If the weights add up to something other than 1, you just divide by the sum of the weights. You see the equation on the screen, and again, you know how to do this. Just the sum of the weights times the actuals for however many periods you're doing, and it's just like computing your average in your course. Here you see another graph. The blue is the same actual data. The orange is a weighted moving average, and you can see it looks very similar to, but not exactly the same as the simple moving average. That's just because the weights are different than they were in a simple moving average. So, how do you pick the weights? Well, for your homework and exams, they'll be given to you. But in general, trial and error is used. You try to pick weights that minimize the forecast error. We haven't talked about how to calculate forecast error yet. If you don't have seasonality, you typically have the last period weighted the heaviest. Having more periods in your moving average gives you more smoothing. Having less periods in your moving average gives you more reaction to changes. Using more periods in your average, quote-unquote, uses up data. So, if you have 10 actual observations and you're doing a 3-period moving average, you're going to end up with 10 minus quantity 3 minus 1, or 8 sets of averages. Do a longer average and you end up with fewer averages. Longer averages tend to hide trends that you might spot with a shorter averaging period. Now let's talk about exponential smoothing. There are actually 3 kinds of exponential smoothing. Simple exponential smoothing, which is what we're going to talk about first. Trend-adjusted exponential smoothing, which we'll talk about later. And Winner's exponential smoothing, which we're not going to talk about because it's a little too complicated. In general, exponential smoothing is the most widely accepted of all the univariate forecasting methods. Univariate forecasting just means all you're using is historical data to do the forecast. Un is Latin for one, so one variable forecasting. It's about the only thing that's used in retail and services. It's very easy to use, it's easy to calculate, it's easy to understand, it's very straightforward, and it does a very good job. So unless you have a good reason to use something else, you should be using one of the exponential smoothing approaches. The 3 approaches are built on clear-cut features including level, trend, and seasonality. Although the 3 approaches to exponential smoothing use different features. Exponential smoothing is less likely to be biased by statistical quirks like outliers. It automatically weights the most recent period the heaviest. It's built into the math, although you might not see it. Surprisingly, there's not any strong statistical theory behind it. It just seems to work. You see two equations for simple exponential smoothing on the screen. They yield identical results, and they're mathematically equivalent to each other. They're just presented differently. I show you both of them because different textbooks use different versions of it. A is the actual, F is the forecast, A minus F is the error term, and alpha is the feedback percentage. It has nothing to do with the alpha that's used in statistics, the probability of a type 1 error. Now let's talk about techniques for trend. While trend can be either linear or nonlinear, we're only going to talk about linear trend. The easiest way to spot a trend is to just plot the data, and note that trends can be positive or negative. When the trend is positive, demand is going up. When the trend is negative, demand is going down. We're going to discuss two approaches for dealing with trend: linear regression and trend-adjusted exponential smoothing. Linear regression is a statistical model that establishes a relationship between a dependent variable and one or more independent variables. For forecasting, the dependent variable is always demand. Simple linear regression is a linear regression with one independent variable. For forecasting, that's almost always just the period number. Some books will call this a trend equation rather than a regression equation. When scientists use regression, there's a real physical relationship between the variables. So the higher your cholesterol level, the more likely you are to have a heart attack. There's an underlying physical relationship there. We can explain it with biology. Likewise, the more you smoke, the more likely you are to have lung cancer. Your sales, or demand, and time are not linked in any underlying way. There's no physical relationship between the two. Rather, time is really just a surrogate for whatever else is going on in the marketplace. When the independent variable is time, that is just the period number, then regression is time series analysis. Simple regression is time series analysis. If any other variable other than time is used as the independent variable, then you have a causal relationship. For example, trying to forecast carpet sales based on the number of new homes being built. When you're using time as the independent variable, there's absolutely no way to spot anything that's changing in the marketplace. So if you're using carpet and housing sales, if housing sales went up, your model would adjust. So if you're using carpet sales and time as your model, if housing starts went up, your model wouldn't adjust. With regression, each observation from the first one to the last one is given the same weight. There are two ways that a book might write the simple regression equation. One is F sub t, the forecasted time period t, is equal to A plus B times t. A is the y-intercept, B is the slope, t is the time period, the 1, 2, 3, 4, 5, the period number. That could also be written as F sub t equals B0 plus B1t, B0 being the intercept, B1 being the slope. That second version of the equation is consistent with statistics textbooks. The models are the same, we're just calling the coefficients by different names. You can find the slope and intercept using Excel and some easy functions. The intercept function will give you the intercept. The slope function will give you the slope. And the correl, C-O-R-R-E-L, will give you the correlation coefficient. You can see a range of period numbers in the A column, cells in the B column. The C column is just applying the regression formula, plugging in a 1 for period 1, a 2 for period 2, and so on to show you how the forecast works. And the formula is used to find those values on the screen. The screen shows our regression forecast. Red is the actual data. The light gray is the forecast. The forecast out of regression is always, always, always a straight line. Simple exponential smoothing does not handle trend well. For that, we turn to trend-adjusted exponential smoothing, which is also known as double exponential smoothing or Holt, H-O-L-T, exponential smoothing. The basic approach is to smooth the data and the trend components separately and then add them together. So this requires two smoothing constants, the alpha, which we're already familiar with, and beta, although not all textbooks call it beta. I've seen textbooks that call it delta. I'm not showing the equations that you need for trend-adjusted exponential smoothing because there's no standard formulas. Different textbooks use slightly different approaches. They tend to give similar but not identical results. What that means is if you're using video tutorials, whether they're on YouTube or my udemy.com MOOC, you need to make sure that the approach being demoed matches the approach in your textbook. On the screen, you see the results of one set of approaches to trend-adjusted exponential smoothing. The blue is the raw data, and the red is the forecast. You can see it picks up the trend. You can also see that it smooths it out, so there's less variation than there was in the raw data. Now we're going to talk about techniques for dealing with seasonality. Seasonality is regular, repeating movements in series values that can be tied to reoccurring events. We tend to think about it as the seasons of the year, but it could be that there's more check cashing at the 15th and the 30th of the month, or there's more demand for parking when events happen. So it could be annual, could be seasons, but it could be other things as well. There are two types of seasonality, additive and multiplicative. With additive, you always either add or subtract a certain amount depending on the season. With multiplicative, you multiply by a percentage called a seasonal relative for each period. Multiplicative seasonality is far, far more common than additive seasonality, and in fact, most textbooks only address multiplicative seasonality. Remember that most companies don't sell to consumers. As such, their view of seasonality may not match what you think of when you think of seasonality. So a common example of seasonality is you sell more lawnmowers in the summer, you sell more snowblowers in the winter. And that's true if you're Home Depot. But it's not true if you're a company that makes those things. Take lawnmowers, for example. You've got to get them manufactured and through distribution in time to get them to Home Depot for the start of the mowing season. That means your period of high demand is prior to the start of the mowing season. Now, if you make the engines for those mowers, you've got to have the engines ready and get them to the manufacturer before they start making the mowers. I've talked to some people in magazine publishing, and, for example, they start putting together their Christmas issue 3 or 4 months before Christmas. So the further up the supply chain you are, the earlier the seasonality applies to you. I'm not going to show actual equations because the techniques are not standardized, just like they weren't with trend-adjusted exponential smoothing. But the general approach is as follows. Use your historical data to compute the seasonal relatives that I mentioned earlier, that is the percentage that sales go up in the summer or down in the winter or whatever they are. Then use your seasonal relatives to deseasonalize the historical data. Use the deseasonalized data to develop a forecast, usually something like regression. And then once you've got your forecast, reseasonalize it. There are two broad approaches to calculating multiplicative seasonal relatives: the centered moving average method and the simple averaging method. The centered moving average method is much more accurate, and in general, it's the preferred method. The simple averaging method is quicker and easier, but it's not nearly as accurate. The screen shows raw data in blue and a sample forecast in red using seasonality. As you can see, it picks up the seasonal variations just great. In general, the steps for computing seasonal relatives with an odd number of periods is as follows. 1. Arrange the data in a single column. 2. Compute moving averages, and you want the number of periods in the moving average to match seasonality. So if it's quarterly seasonality, you do a 4-period moving average. 3. Divide the demand by the moving averages. You won't have a moving average for all periods, so you skip the ones where you don't have both the data and the moving average. Once you have those, average the values from step 3 for each period. So for all the summer periods, average them together. For all the winter periods, average those together. Those percentages will be your seasonal relatives. Then you want to produce your forecast. And finally, seasonalize the forecast. The steps are the same when you have an even number of periods, except you have to add a step. Between what were steps 2 and 3, you have to do a 2-period moving average. I'm not going to go in details about how to do that or why to do that, but it's covered in the video tutorials that I have mentioned. The steps to computing a simple averaging method. 1 is to arrange the data in a grid. So you might have quarters in columns and years in rows, for example. Compute a row average, average the row averages, and divide each row average by the overall average. That gives you your seasonal relatives. Now let's talk about cycles. Here we're talking about long-term economic cycles. Cycles are up and down long-term movements, basically a series of economic expansions and contractions. They're typically 3 to 7 years. They're not uniform, they're not predictable. And because they're such a long cycle, by the time you have one full cycle, the market has changed so much it's not really possible to predict the cycle for the next time. So it's difficult or impossible to use them in forecasting. Most of the time, we simply ignore them. If you have an explainer variable or a leading or lagging variable, you might be able to use them, but that's not typical. I have mentioned this before, but associative techniques use related variables to predict variables of interest. The example I gave earlier was using new housing starts to predict carpet sales. At Georgia Power Company, we used new housing starts to predict increases in residential electric sales. This isn't as easy as it sounds. If you want a forecast that goes 5 years out into the future, say for carpet sales, then the first thing you have to do is forecast new housing starts going out 5 years because you're using the new housing starts to forecast the carpet sales. So using an associative technique just raises the number of forecasts that you have to do. The most common approach for associative forecasting is regression. If you're using one variable, it's simple regression. If you're using 2 or more variables, it's multiple regression. Correlation, which goes from -1 to +1, can tell you the strength of the relationship between the dependent variable and each one of your independent variables if you have more than one. Indicators are variables that precede changes in a variable of interest. These are also known as leading indicators. With my example of new housing starts and residential electric consumption, the houses have to be started and built before they start consuming electricity, so that's a leading indicator. These indicators can help improve forecast accuracy, but if you're going out long term again, as I mentioned, you have to forecast them. They're also lagging variables. You can use these to help forecasting, but they're more difficult to use than leading indicators. My students can access the video tutorials for these problems using the content menu in D2L. YouTube viewers can access the video tutorials on my MOOC on udemy.com. I have a long and short version of the URL posted on the screen, and I will post this URL in the description. The next lecture in this series is forecast accuracy. I will see you then. If you enjoyed this video, please click like and consider subscribing to this channel.